yeah, let's see what we covered in our last lecture. Let's make sure it's recording. Yes. Okay, today's our last lecture, right? So we're gonna finish no matter what. Okay. So, yeah, in our last lecture, so we cover those topics. So first, we finished talking about the rate distortion function of the binary source, right, with Hamming distance. Okay, so this is one very specific combination, and we're still using that today. Okay, and so this is the equation. So basically, we proved that in our last lecture, right? So if you forgot, just take a look. And we're going to have something similar for the final exam. Okay. And then we move to the Gaussian source with the squared error distortion. So here, so before we cover for the theorem, we talk about the discrete memoryless source, right? But we say, okay, the same idea would be can be used, and the same theorem can be extended to the continuous source as well, right? So then we talk about the Gaussian source, right? It's a continuous source. Okay, and when we talk about Gaussian source, normally we use a square distortion measure. Okay, so we don't have all the combinations. So for Gaussian source, we can now use the Hamming distance or the Hamming distortion, right? Because, yeah, for the obvious reason, right? So we can now say this, and whatever is equal, or we don't say that. All right, so and then so this is the formula. So the idea is very, very similar to before, right? If you forgot, just take a look at the lecture note. Okay, and then we cover the geometric interpretation of the rate distortion theorem, right? So basically, this is the sphere covering lemma, right? So before, for the capacity, it's sphere packing, right? So given a sphere volume, right, we want to see how many spheres can be fit in. So that's sphere packing, right? But here we have a sphere which represents our source, right? And then we found the minimum number of sphere to cover those. Okay, so that's basically the idea. All right, and then we talk a little bit on the analytical approach for the computing the rate distortion function, right? And so basically, we can write the rate distortion function, write the mutual information as this, right? And then we have some constraint here, right? And we proved that before. So for the mutual information, so by fixed px, so it is the what? Convex function of q x hat given x, right? Therefore, and also for this, all the constraints are linear constraint here, right? Therefore, we can say that so this function, so this optimization problem is a convex optimization problem, okay? And then we can use the KKT condition to solve it. And actually, we did use the KKT condition to solve it. And you can check in the book. It's not in extremely detail, but the idea are there. So you can just take a look at, we can get some closed form expression for the rate distortion function. Okay. All right, and then we talk a little bit on the Arimoto-Blackwood algorithm. So basically, yeah, so this is another approach to compute the rate distortion function. Okay. So yeah, this is kind of like, this is a bi-level optimization algorithm. So the key idea here is that, we want to use this kind of algorithm, right? So basically, so this kind of algorithm, so the example given class is that, okay, so if this is a convex set, and this is another convex set, and then how to find, the 2 points that are the closest, right? So basically, the idea is that we fix one point here, and then find the closest point on this set, and then repeat this process until they converge. And then we can find this 2 points, right? So I want to use this kind of idea for computing the rate distortion function. Okay. So how can we use this idea? So basically, we need to find, okay, these 2 optimization problems, and each of them has one variable. Okay. And here we can see that. So for the rate distortion problem, we only have one variable, which is px hat given x. Right. We don't have 2. Okay. Then how can we apply this approach? Right. So we stop right there. So yeah, we're going to continue talking about that in this class. All right, so let's see. Okay, so today, It's our last lecture. Okay, yeah, for who came late, just fill up the course evaluation if possible, right? So the due date is very soon. I think it's this Friday, right? So yeah, if I have not done that, just do that as soon as possible. All right, so yeah, let's see how we can do that. Okay, so in order to do that, we need to introduce a few lemmas. Yeah, so let's see what we're going to cover today. So the first one is Arimoto Blahood algorithm. And the second topic is we're going to talk about the separation theorem. So this is very similar to before, right? So now I want to transmit the source via a channel, right? Should we do the joint source channel coding, or should we do that separately? Okay. And then lastly, we're going to talk about parallel Gaussian sources. Okay, you may expect that for the parallel Gaussian channel, so we have the water filling algorithm, right, to design to allocate the power, right. So here, we consider a parallel source, okay, and then you can see what we want to distribute over them to maximize the redistortion. Okay, so basically we're going to design the distortion for each source, right. So basically the idea is that, okay, if yeah, let's talk about that later. So it's kind of long. All right, so yeah, let's see. For the first topic, the Arimoto Blahood. So we need to introduce some lemma here. Okay, as we said before, so basically the idea is to introduce another variable so that we can do this iterative algorithm, right? So then we need to use, we have a very interesting idea. So basically for the mutual information, so actually we can write that as follows. The inf over ry, so for some distribution ry, d px py given x, and px ry. Okay, so yes, so this basically tells you that, okay, so for some distribution ry, if we do the minimization of the relative entropy between this guy, and then you get the mutual information. Okay, clearly, if ry equals to py, then it will be the mutual information, right? So actually, we can show that the mutual information is actually, is a result of this minimization problem. Okay, and the best ry star, so that's equal to this guy. Okay, and that's ry. So we write everything in terms of px and py given x. All right, so yeah, this is the lemma one, okay? And so by using this lemma, so we can turn our original problem into this an optimization problem, but over two variables, okay, over two distributions, right? So basically, in this case, we can write RD, as the first infimum is over this guy, subject to a distortion measure. Right, the second infimum is over ry. So ry is basically our x hat now. And d of px hat given x, and here is px hat, rx hat. Okay. Then we turn a problem from one variable now to two variables. So we have this variable and this variable, okay? Okay. So then we can use the idea we introduced before, to do this, iterative algorithm, okay? So we're going to introduce that later. And now let's go back to our channel capacity maximization problem, right? Can we do anything similar? Okay. So basically, now let's introduce our lemma 2. So which is very similar to lemma 1, right? So basically here, what we're doing is that, so for the channel capacity problem, so for the mutual, can we write the mutual information of some maximization problem? Okay, so basically we can, actually the answer is yes, we can do that. So basically what we can do is that we can write that as a sup over R x given y of the following. Sum over xy px py given x log R x given y over px. Okay, that's also relative entropy, right? So, but we can break it down, and then write that in this way, okay? And then clearly, so what is this guy? What is the optimal value? So you may imagine that's px given y, right? So basically, that is this guy. Py given x divided by the marginal distribution. Okay, so basically, therefore, in this way, for the channel capacity problem, right, we can write the C, which is channel capacity, is a supremum of the mutual information over Px, right? So that is, I have two sup here, right? The first sup is over Px, and second sup is over Rx given y, and then we have this. Okay. And if you compare those two, again, they're like a dual problem, right? They look very similar. So basically, one algorithm, so to design an algorithm to characterize the channel, the rate distortion, and the algorithm to characterize the channel capacity are pretty similar. Okay, so that's why I have two names on the algorithm. It's called Arimoto-Blahood algorithm. So there are two persons. Okay, so for the rate distortion one, so that's Blahood algorithm. And for the capacity one, it's an Arimoto algorithm, okay? But the idea is exactly the same, so we do not distinguish them very much. Okay, so first let's see what is the Blahood algorithm. Oh, by the way, so we didn't prove that. How can you prove it? Any idea? Or, prove this. Yeah, think about it, right? Yeah, it's not that hard. So basically, what we do is that, so, this is a KL divergence, and this is another KL divergence, right? So basically, we want to show that this guy is always bigger than that, right? And then when we take the infimum, and then they're equal, right? It's like, we prove something is bigger than or equal to 0, and when the equality holds, and then we need some condition. Does that sound familiar? Yeah, did we do that before? Prove something is bigger than or equal to 0, and then see when the equality to 0 can be achieved. Yeah, when?
We do that a lot.
Yeah, we do that a lot. Give me an example. The first example, we have seen that. It's the KL divergence, right? We show the KL divergence can be bigger than 0, right? And we use this property to prove a lot. For example, we prove the cardinality upper bound of entropy, right? Same thing here, okay? We just compute the difference between these two. And if you compute the difference, and then you'll see another KL divergence term will come out. right? And then automatically it's bigger than or equal to 0. Okay, when that equal to 0 is when this condition holds. It's very straightforward. Okay, and the same thing here. So so yeah, just take a look at the book. If you may just a few lines of proof. Okay, great. Yeah, let's introduce the Blackwood algorithm. Okay, so yeah, I'll just write the Blackwood algorithm, and then yeah, you can see how we can derive it, right? We have a few steps here. The first step is that, so we start with and gamma 0, yeah, R0, yes. Okay, and secondly, so here we need to compute two things, right? One is px hat given x, the other is rx hat, right? So okay, so now if we start from rx hat, so it's like we have, oh yeah, so it's not the other one. We have two sets to begin. We have two sets there, right? We just begin with one set, right? Here we begin with the r there, okay, and then from r we could compute p, right? So second step is that, so we can compute this guy. So we have a time index of L here. So L means the first step or second step and so on, right? The step index. So this guy will equals to what? So this, normally we don't know that, right? But what we can do is that, so because we know this analytical approach, right? We didn't talk about that in detail, but if we follow the steps of the analytical approach, so we can get an analytical expression for this. So it's given by the follows. So it's RL minus 1 x hat and E minus lambda dx x hat and divided by this. Okay, so this is the formula. Okay, so this is given by the analytical approach, right? As we said before, so normally the analytical approach cannot give you the RD directly, right? So we can see some property there, but we cannot evaluate that directly. Okay, so this algorithm gives you how to use the analytical approach to get the RD. Okay, and so this is the formula introduced by the analytical approach, right? And we can see that because we start from here, so this guy is known already, right? Therefore, we can compute that, okay? So you may imagine what is lambda here. So normally, what is a lambda in our class? The lambda is normally the Lagrange multiplier, okay? And here, in particular, the Lagrange multiplier lambda is minus RD derivative, minus the derivative of RD, right? Therefore, for different lambda, you will get different points on the RD, okay? You just do that for each lambda, and then you'll get all the points, okay? After that, the third step, we're going to compute the Rx hat, right? So the L x hat, so that is given by this guy, right? So we can get that from our optimization problem, right? So this guy equals to the sum of px and pl x hat given x. Okay, right? And then we're going to run this algorithm until some requirement is, or some criteria is satisfied, right? Normally, we run that until something doesn't change anymore. Okay, until some stopping criterion is satisfied. Okay, yeah, and then we stop. Okay, so otherwise, we're going back to step 2. Okay, and keep running this algorithm. That makes sense? Okay, great. All right, so yeah, this is basically the Blackwood algorithm, and we can show that the algorithm will converge to the optimal RD, right? As we said before, this algorithm may not converge to the optimal value, right? As we said, right, let's say if we have two convex set and then the metric is distance, then we can show it will converge to the best, to the global optimal, right? So here we can show the same thing. Okay, so this algorithm can converge to RD. Okay, so let's emphasize it here. So we can show that, so this algorithm converges to RD. Okay, so as L goes to infinity. Okay, great. And any questions? Okay, yeah, for the Arimoto algorithm, so I will not talk about that. Arimoto. So you can take a look at the book. So the idea is exactly the same, right? We just work on a different formula, right? And there's a few other forms of Blackwood algorithm. This is not the only form, okay? You can check it in the book or online to see other form of it, right? But the idea is similar. Okay, great. So this is Arimoto Blackwood algorithm. So now by using this approach, so we cannot compute the function analytically. I mean, yeah, analytically, but we can compute the function numerically. Okay. Oh, by the way, so there's a very recent work from Google. It's called TurboQuant, right? So that provides you because now in the large language model, compression is extremely important, especially for the KV cache, right? So they introduced, I think the paper was last year. So they consider a kind of old-fashioned vector quantization problem, right? And then they provide a very interesting algorithm. So you can take a look at that. So it's called TurboQuant. Right, so it's an interesting algorithm that you may want to take a look. Okay, so this is very relevant today. Okay, so it's very important. Second topic is the separation theorem. So we're not going to focus on that here because we have seen that before. Okay, so now the only difference here is that we have a distortion metric D, right? Before we do not have it, now we have it, right? So before we want to characterize, the rate of the compression. Now I want to characterize the rate of we want to characterize the rate distortion. Okay, so basically the problem is the same as before. So I have a source. So now the source means, we have an arbitrary distribution of the source. Okay, and then we have an encoder. So that we have xn, vk, right? And then we're going to use this code to transmit, right? So then we have a channel here. So characterize at p y given x, right? And then we have our yn. Okay, and then so we have the decoder. Okay, and then we have our vk hat. Okay, so this is basically the whole problem, right? So as we introduced before, or we call that the joint source channel coding, right? So as we discussed before, so we can use the separate algorithm, the separation theorem, right? So basically, for the the separate source channel coding algorithm, so that's achievability. So what we can do here is that we have the source, right? We can have a source code, source coder, source. We can have a source encoder, and then we can have some indices, source coding m, right? And then we have a channel encoder. Right, and then we can have a channel code word, right? And then we're passing that through a channel, right? And then we got some received signal, right? And we'll pass that through a channel decoder. And then we can have a m hat, right? And then we pass that through a source decoder. And then we have our vk hat. Okay, so this is the separate source channel coding. Okay, so as we said before, so if there's no distortion, so technically we do not have any loss in terms of the rate here. Okay, so basically what we have shown before is that so basically so it's the rate. We do not have any loss for the rate, right? But here now, if you consider the rate distortion, so can we still claim the same thing? Right. So before, what do we have is, do you remember? So what is the separation theorem tells you? Anybody remember it?
That you can do them separately.
Yeah. So, but what's the formula? Yeah, how to remember it, right? So the source have like block length of k, right? It is like k entropy less than what? N times capacity, right? So that's the best you can do, right? As long as you can guarantee this is less than that, then we're okay, right? We're equal, right? Does that make sense? So basically, so this is source entropy, and then if you times that with k, so that's the total information at the source. Let's consider DMC, okay, for simplicity, right? And then, so for the channel, right? So this is a channel capacity per channel use, and the length of the code is n, right? So this is like how many you can transmit for n channel uses, and as long as this is less than that, and then we're okay. Very intuitive, right? And then the separation can give you this, okay. Therefore, we say okay, there's no gain if we do the separation, right? Of course, we can get some complexity gain, but from the capacity point of view, there's no gain, right? But so here we have the same thing here, right? So basically, and normally what we do is that for this guy, so we can have this is less than or equal to n over k, right? And then this equal to tau times c, right? We define tau as this guy, right? So here we have the same thing, right? Rd will be less than or equal to tau times c, and then we're okay. Okay, how to prove that? So we proved that already. So this is achievability, right? So we proved the achievable part already. You can follow the exact same argument and to prove that, but this is the idea, right? And for the converse, it's also very, very similar, some of the same. Okay, so you can take a look at the book. But the idea is here, right? So there's no gain in terms of the capacity. Does that make sense? Okay, yeah, that's relatively straightforward. Okay, so now let's take a look at the last part of the class. So it's a parallel Gaussian sources. Okay, so yeah, for this guy, so now instead of consider just a one Gaussian source, we consider a number of Gaussian sources, but they're independent, like what we considered for the parallel Gaussian channel, right? All the channels are independent, there's no correlation, right? But if there is a correlation, it's not a big deal. We do whitening here, same thing, right? So correlation will not bother us. Okay, so basically we are considering some independent Gaussian sources. Okay, so consider independent Gaussian sources, x1, x2, up to xn. Okay, and we assume that each xi will follow a Gaussian distribution, 0 sigma I square. Okay, and they'll assume that they're independent, right? So equivalently, so what we consider is kind of like a Gaussian vector, but the covariance matrix is a diagonal matrix, right? So equivalently, we consider a vector, Gaussian sources. Okay, so xn will follow a Gaussian distribution with 0 and k, where k is a covariance matrix, right? And then k here is equals to a diagonal matrix, sigma 1 square, sigma 2 square, up to sigma n square, and all 0 here. Okay. So this is the source, right? So now we need to define the distortion, right? Again, we have this square error distortion. So distortion is defined by this. dx and x hat is given by the sum over I, and then xi minus xi square. Okay, again, so this is additive distortion, so as we introduced before. Okay, so we can write that as a norm of this. Okay, and you can see that for each source, so it's basically a Gaussian source with a distortion of the square error distortion, right? So any questions so far? Okay, good. So yeah, this is pretty straightforward. Okay. All right, so now let's characterize the redistortion function for this guy. Okay, obviously, so although it's a parallel sources, but we consider that as a vector quantization. Okay, so the whole thing is a source, right? Therefore, so we are not going to do that individually, right? Because of what? Right. So we can now just say, okay, characterize the redistortion function each individually, right? Because we have a joint distortion here. Okay. Therefore, so we need to think about how can we allocate the distortion for each source such that the total distortion can be less than or equal to d, right? So that's basically the idea. Okay. So the RD will be equals to that. We are going to minimize over x hat given x, right? And then the distortion is this. Okay. Yeah, I'm using a different index compared to my different notation in my notes. So, yeah. Xn minus x hat n squared. So that less than or equal to d, right? And then, so yeah, I'm using m here. Okay. So then we're going to minimize that over this mutual information. Right? So that's our optimization problem. Okay, so we're going to optimize it. So the idea is the same as before, right? So we don't use an analytical approach. So we're going to do whatever we did before. Okay, so basically we're going to characterize the lower bound of the mutual information and see when the equality the equality will hold. Okay, so basically, so this is what we do. Yeah, characterize this mutual information, right? So for this kind of problem, we only do this way. Okay, right? So now, so before it's easy, we just have a scalar here, right? So we can just remove this and then we get a lower bound and so on, right? But here it's a vector, right? So vector, we cannot do that directly. So what we do here is chain rule, right? So by using the chain rule, so what we get is this. Given, so we only do chain rule over this. Okay, and keep m hat. Okay, any questions? Okay, and then, so yeah, similar. So before we just drop, drop the condition here, right? So here we can basically do the same thing, right? So basically what we're going to do is that we're going to drop some of the condition, right? So what we want is what? Want to go back to what we have seen before, right? What we have seen before is this one, right? So will this bigger than or equal to hold? Yeah, will that hold? So basically, I just want to compare this guy and this guy. Which one's bigger, right? Yeah, which one's bigger? Yeah, exactly. Right, condition will reduce the entropy. Okay, so this will become bigger, then we'll have a lower bound, so no problem. Okay, and then now the problem is much better, right? So let's see. Yeah, so this basically equals to this. Right, because all x's are independent, right? And then we have something that we're really familiar with, right? So I have the mutual information here. Any questions? Good. Okay, then what do we do? So basically, so this is something we know already, right? Right? So we know how to minimize that, right? So this will be bigger than or equal to of this guy, right? Log sigma I squared divided by di, right? And then we just take the positive part, right? If it's less than 0, just use 0. So this notation basically means, so this means the max between 0 and this. Okay, so it's bigger than 0, it is whatever, but if it's less than 0, it just takes 0. So any question for this? Okay. Okay, great. And now let's see how we can achieve that. How we can achieve that? Right. First of all, this is fine, right? Because as long as given x hat, and then so we can determine xi, and then we're good, right? So we're gonna see that this can be done, and this is okay, right? We show this is achievable, right? How to achieve it? So we can use the backward channel, right? Right. So basically, what we do is as follows. So basically, we just let xi equals to xi hat plus ei, right? Use the backward channel idea, right? So now we just need to we just make sure assume that ei and xi are independent. Ei is the error of the noise, right? They are independent, and then all of them follow a Gaussian distribution, right? So basically, ei will follow a Gaussian distribution with 0, and the distortion, right? Hopefully, I still remember how we derive it. So xi will follow a Gaussian distribution with sigma I squared minus di, right? And we'll make sure that they're independent. Okay, so the ei and xi hat are independent. Okay, and by doing that, we can show the lower bound can be achieved, right? So that'll be our distortion. Okay, rate distortion function. So now the problem becomes now want to minimize this guy, sigma I squared plus di, right? And subject to the summation of all the distortion, di would be less than or equal to d, right? And then we'll have a condition that di has to be bigger than or equal to 0, and less than or equal to this one, right? Otherwise, it will be 0. Is that clear? So now, we want to solve this optimization problem. Okay, again, so this is a convex function, right? And all the constraints are linear, so it's a convex optimization problem. How to solve it? KKT condition. Okay, again, the same thing. So basically, we're going to do the follows. Okay, so basically for the KKT condition, so we're going to let J, we have D1 up to Dn, and now we have lambda. So this is our Lagrange multiplier function, right? So this is given by, right? And then we just add the Lagrange multiplier lambda. We always use lambda for that. Okay, and then we use di minus d. Okay, again, it's bigger than or equal to 0. Okay, yeah, we just ignore this bigger than or equal to 0 condition, so we can add it back. It doesn't matter because we have a theorem, without it, and then we can have very nice result. Okay, so in order to solve this problem, we just want to compute the derivative and see when it's equal to 0, then we're fine. If it's less than 0, then we have to pick 0. Okay, so that's basically the idea. Okay, so now let's do a derivative. Compute the derivative of J respect to di, okay, and see what we can get. Okay, and now there's only one term here, so that's half di over sigma I squared, right? We need to inverse it. So we just assume that the log is based on E, so for simplicity. And then multiply sigma I squared divided by d squared, and then multiply minus 1 plus lambda. Okay, so this equals to half di plus lambda. A lot of things can be canceled, right? So you can see that. So this will be canceled, this will be canceled, this will be canceled. Okay, so very good. So now we have two cases to consider. Let's say if this guy is less than this, right? So basically, then we can achieve 0 here, right? So this basically means that, let's say if you consider a convex function, it'll look something like this, right? Let's say if sigma is here, and then this guy is whatever di, the optimal value can be achieved, right? On the other hand, so let's see, we have something here, right? But sigma I is here, right? So it basically means that the minimum point cannot be achieved because di has to be less than sigma square, right? Then, so the second case is di is bigger than sigma I square, and then so we don't have any choice. You want to achieve the minimal, so the derivative has to be less than 0, which means that so the di has to equal to sigma square, right? So yeah, here is already the minimal, right? This cannot be achieved, right? For the first case, so we can see that di will equals to 1 over 2 lambda, right? And the lambda is just Lagrange multiplier, doesn't matter. We'll set the whole thing equal to nu, right? So that should look familiar, right? We used this notation before. All right, so given by this, so now we solve the problem, right? Therefore, di is just equals to the minimum over nu and the sigma I square, right? And we need to make sure that the sum of all the di, right, equals to the sum of all this minimum between nu and sigma I square. So this has to equals to d, right? So that's our distortion. Okay, and in this case, under this condition, Rd can be satisfied, right? Rd equals to this. Okay, and we're done. Okay, yeah, that's the last thing for our class. Okay, great. So now we need to see what's the meaning of it, right? So did you remember what's the meaning for the channel capacity? It's a water filling, right? Yeah. Right, so I have a nu there, and then we need to fill the water up to nu, right? So let's see what's the meaning in this case, okay? So here, So let's say what we do is like this. Okay, so now let's say here is a sigma I here, and here yeah, it's a distortion. Okay, so basically, let's see what's the meaning here. Okay, so let's characterize in this way. Okay, let's say, okay, so what if we have the variance distribution? Yeah, here's not distortion. Here's the variance. Sorry, here's the variance. Let's see, the variance distribution is like this. Yeah, let's say we have like whatever is enough, 1, 2, 3, 4, 5. 5 sources, okay, and this is sigma 1 square, sigma 2 square, sigma 3 square, and so on. Okay, so now we have a new, right? So let's pick a new in an interesting point. So let's pick a new like maybe here. So that's our new, right? So what does that tell you? Let's say for the first one, so sigma I is bigger than nu, right? So then the distortion would be what? Nu, right? And yep, and so the distortion will be here, yes. Okay, and for the second one, again, so sigma is bigger than nu, right? So distortion would be here. Okay, and the third one, the distortion will be here, right? But for this one, what happened? Yeah, so nu would be the distortion, right? And for this one, so basically the rate distortion function will be given 0, right? Similar for this one. Yeah, for our design, so we can see that for the x hat, so this would be the distribution of our x hat, right? So it basically means that, so this guy, let me use another color. So this guy can be understood as a new sigma for x hat, or we call that sigma I hat, right? So that's basically the variance for our reconstruction codebook. Okay, so in this figure, let's see where that is, right? So that equals to what? Sigma minus the distortion, right? So basically for the first guy, it is here, right? So that's the variance for the reconstruction codebook x hat, right? And for the second one, so this would be the variance, right? And for the third one, so this will be the variance. But for this and that, the variance is 0. Right, we don't have, it doesn't matter, it can be deterministic, whatever, right? So does that look like a water filling? Right, before water filling is that we take the bottom part, right, we fill water. But here the water level is here, right? But what we're filling is like actually here.
So it's upside down water filling.
Exactly. So we have a name for that. It's called reverse water filling. Algorithm, right? So that's for the source coding problem. Okay, again, so this is like very dual problem of the channel coding, right? Channel coding will have water filling. This guy will have reverse water filling. Okay, great, and that is everything. So very last thing. Okay, so we don't have time to cover anything about network information theory. So by network information theory, is to talk about the real network, right? For example, how about, let's say, we have 2 sources, okay, and then can we encode them together? Okay, or let's say we have like a communication problem, one transmitter and 2 receiver, right? Let's say we have a shared medium, right? How can we to do this kind of transmission, or vice versa, right? This is a broadcast channel. We can do either this way or the other way. So the other way is called the multiple access channel, right? So for all this kind of problem, we don't have time to talk about that, obviously. But I have a lecture notes to talk about this problem. So it's called sleeping wolf coding problem. So it's very, very interesting coding problem. Actually, if there are some correlation among the sources, and then we can save a lot here, right? But what is very interesting is that we can do the coding separately. We can still save a lot. So they don't need to talk to each other. Okay, so kind of very counterintuitive but interesting problem. So I'll upload my lecture notes, right? So we're not going to test you on this for the final exam, but if you're interested, you can take a look at my lecture notes, lecture video. Okay, great. Yeah, thank you for the semester. So hopefully you have a good time for the class.
Yeah,
Yeah, thank you.